Hello students. In this lecture we are going to study the effective stress and neutral stress with respect to variation in water table. What is the effect of this variation in water table on these two stresses? Also, when the soil is partially saturated, then above the water table sometimes water is rising by capillary action. So what is the effect of this capillary rise on these two stresses? And also we are going to study that when the soil is loaded with some external loads acting like surcharge, for example load due to railway track or load due to some structure, then how does these external loads which are acting on the soil in the form of surcharge, they cause their effect on effective stress and neutral stress, that we are going to study in this lecture. In this initial slide, we can see in figure 1 different cases for effective water table, capillary action and surcharge. In figure 1a, we can see the water table level is above ground level, which is the lake condition. In figure 1b, we can see that the ground water table level is at the ground level. In figure 1c, we can see that groundwater level is below ground level and there is some capillary zone, and in figure 1d we can see that some form of loading in the form of railway track or some structure is acting in the form of surcharge intensity at the ground level. So in this first case, there is a lake water above the ground level to a depth of 2 meters, and then the soil layer under consideration is 5 meters, and the saturated unit weight of this particular soil is 20 kilonewton per meter cube. Unit weight of water gamma W 10 kilonewton per meter cube, and the soil is degree of saturation of the soil is 100%. So let us come to the calculations. Above A there is no load, so total stress at A is 0. Then at B the load of water is acting at this level, and therefore the soil has to carry this particular load. So unit weight of water is 10 kilonewton per meter cube and the height of the water is 2 meters. So it is 10 into 2, 20 kilonewton per meter square is the stress at the level B, total stress at the level B. Then the total stress at the level C will be this 20 which will be carried forward coming from the top, plus from B to C the load is saturated unit weight of soil 20 into height of soil layer 5. So 20 into 5, 100 plus 20, that is 120 kilonewton per meter square of total stress acting at the level of C, that is the base level of the layer. Coming to the neutral stress, above level A there is no load, so again neutral stress is 0. Above level B there is a water standing to a depth of 2 meters, so 10 into 2, 20 kilonewton per meter square will be the neutral stress, as the water table level is 2 meter above the ground level. So at B the neutral stress will be 10 into 2, that is 20 kilonewton per meter square, and the neutral stress at the level C will be 20 coming from the top plus 10 into 5, that is 50. So 50 plus 20 is 70 kilonewton per meter square. Effective stress is the difference between total stress and neutral stress. So 0 minus 0. So effective stress will be 0 at A, then 20 minus 20. So effective stress will be 0 at B also, and at C it will be 120 minus 70, which is equal to 50 kilonewton per meter square. Let us go to the next case where the groundwater table is at a ground level itself, and therefore if we consider the same values, that is saturated unit weight is 20 kilonewton per meter cube, and unit weight of water as 10 kilonewton per meter cube, and degree of saturation is 100%. Then coming to the calculations, above level A there is no load, so all the three stresses will be 0 as we have seen earlier. At the level B it will be 20 into 5, that is 100 kilonewton per meter square. Neutral stress will be unit weight of water 10 into 5, so 50 kilonewton per meter square, and therefore the difference in these two is 50 kilonewton per meter square. at B effective stress will be 50 kilonewton. So these are the stress diagrams. Sigma diagram means total stress diagram, U diagrams neutral stress or forced water pressure diagram, and sigma dash, that is effective stress diagram. Let us come to the next case where the capillary zone exists. Now there are certain types of soils like fine sand, silt or clay, which are very fine grained soils, and being fine grained, the voids between them have very less size, and therefore these void spaces, they are acting like a capillary tube. So as water rises in the capillary tube due to capillary action, in the same way water also rises above the groundwater table. As you can observe in this figure 4, water is rising above the groundwater table level up to some height because of this capillary action, and the height for which the water is rising is known as capillary zone, and this height is represented by HC, and it is 1 meter in this example. So the properties of soil are above this capillary zone as the degree of saturation is 40%. It is not zero. Soil is not total dry. So we cannot take dry unit weight of the soil, but we have to consider the bulk unit weight of the soil, that is 18 kilonewton per meter cube. Then the properties of soil within the capillary zone are saturated unit weight of the soil as 20 kilonewton per meter cube and degree of saturation as 100%. And below the water table, the saturated unit weight is again 20 kilonewton per meter cube and degree of saturation is 100%. So let us go to the calculation table. Now above level A there is no load, therefore the all the stresses, that is total, neutral and effective stresses, are zero at level A, which we have seen in the earlier cases. At level B, which is at the level of 3 meter from the top, from the below the ground level, the unit weight of the soil, that is bulk unit weight of the soil, is 18 kilonewton per meter cube, and therefore the total stress is 18 into 3, that is 54 kilonewton per meter square. At level C, the load from A to B is to be added to the load from B to C. So that load is 54, which is coming from the top, and zone BC is 1 meter in depth, and unit weight of soil, which is saturated unit weight, is 20. Therefore 54 plus this 20 will give us the total stress of 74 at the level of C. When we go to the level of D, then this layer, zone CD, is again 1 meter zone. Unit weight is same, gamma sat 20. Therefore, when we add this 20 into 1, that is 20 to 74 coming from the top, we get a total stress of 94 kilonewton per meter square. Neutral stress in this case, as water doesn't exist from A to B, so neutral stress at A will be 0. But here in this zone from B to C, water is rising against gravity, and therefore the neutral stress will have the negative sign, that is minus 1 into unit weight of water 10. So minus 10 kilonewton per meter square will be the neutral stress at level B. At level C, groundwater table level is there, and always at groundwater table level the neutral stress is 0. So because of that, neutral stress at level C will be 0. And then for the remaining depth of 1 meter below the groundwater table, that 1 meter into unit weight of water 10 gives us the neutral stress of 10 kilonewton per meter square. And therefore, we can see the effective stress is 0 minus 0, 0 at A. At B, 54 minus minus 10. That means 54 plus 10, which comes to 64. So we can see here, when capillary rise is there, we get increased effective stress, which is more than the total stress at level where the capillary zone ends. At its upper face, we get more effective stress as compared to the total stress. Then at level C, 74 minus 0, that is same 74 kilonewton per meter square of effective stress will act, and at level D 94 minus 10, so effective stress will be 84. So we can see in this diagram, sigma diagram, U diagram and sigma dash diagram. See 0, 54, 74, 94, 0, 54, 54 plus 7, 20, that is 74, and 94 at the base. Neutral stress diagram minus 10, 0 at the level C, that is at groundwater table level, and at the base of soil layer it is plus 10 kilonewton per meter square, and therefore the effective stress diagram is like this: 0 at A, 64 at level B, 74 at level C, and 84 at level D. Let us go to the next case. Now, if the soil is not a fine grained soil, if let us say coarse grained sand is there, which is having its grain size greater than, let us say, 2 mm or even greater than that. So coarse sand or gravel soil layer is there, then in that case, of course, whilst being larger in size, no capillary action will take place and there will not be any capillary rise. Then in this situation, if the groundwater table is below the ground level, then again let us consider the similar values, that is degree of saturation 40%, so bulk unit weight 18 kilonewton per meter cube above groundwater table, and below the groundwater table saturated unit weight is 20 kilonewton per meter cube and degree of saturation let us consider as 100%. Therefore, coming to the estimation table, values at level A, as there is no load above, so all the three stresses will be 0. At level B, it will be bulk unit weight 18 into depth of soil is 5 meters, so 90, 18 5s are 90, and water table starts from level B below. So at groundwater table level, that is at B, neutral stress will be 0, and therefore effective stress 90 minus 0 will be 90. At level C, this 2 meter into 20, so 20 into 2, 40 will be added to this 90 coming from the top. So the total stress at level C will be 130 kilonewton per meter square. Water depth is 2 meters, so 10 kilonewton per meter cube. Unit weight of water multiplied by this 2 meter of depth will give us the neutral stress of 20, and therefore 130 minus 20 will be the effective stress, which will be equal to 110 kilonewton per meter square. Let us come to the final case, which we can see in figure 6, where at the ground level, surcharge of intensity 20 kilonewton per meter square is acting. Groundwater level is also at the ground level, and the properties of soil we are observing as gamma sat 20 kilonewton per meter cube and degree of saturation 100. Then in this case, this surcharge is going to have its effect throughout the depth of soil. So this 20 kilonewton per meter square of intensity of surcharge will be represented by rectangle, as you can see in this total stress diagram, and there is no load of soil above level A. So total stress due to soil is 0 at A, and therefore the total stress at level A will be 20. At level B, the soil is saturated, so 20 into 5, that is 100 plus 20 coming from the top, which is due to surcharge intensity. So the total stress at level B is 120 kilonewton per meter square. The depth of water from A to B is 5 meters, so 10 kilonewton per meter cube, which is the unit weight of water, into 5 gives us neutral stress of 50 kilonewton per meter square, and effective stress, therefore 120 minus 50, that is 70 kilonewton per meter square at the base of the soil layer. So after studying the basic principles of estimation of effective stresses and neutral stresses in case of different possibilities of hydraulic conditions and different loading conditions, you will now be able to estimate these stresses in case of various possible combinations of these conditions. In the next lecture, we are going to learn about the seepage pressure, critical hydraulic gradient, and quicksand condition.